101, you need to know it. And if you have your books, you can look at page 410 for reference. I'm just going to tell you that I prefer when I'm doing problems, or whenever I'm doing developing something that we use as one of those equations, I go from first principles. In other words, Maxwell's equations and develop them. For these waveguides, fiber optic or just cylindrical waveguides, or slab waveguides, in Dr. Wentworth's book, he does not do the full development. And the reason is this, is the solutions are more complicated. They're a lot more complicated, and they are series solutions that require, do you know what a transcendental equation is? It means an equation that doesn't have a closed form solution. You find the intersection of two, say, plots, all right? And the point where they intersect on, say, the x-axis would be the solution. But there's no closed form of that. So these are much more difficult. That's why Wentworth's book doesn't really cover slab waveguides or dielectric waveguide, or I should say, or cylindrical waveguides at real depth for Maxwell's equations. But I want to do this start. I'm going to start with the actual fiber optic. And put down cylindrical guide. And it's a dielectric guide. Now, last time I said what a fiber optic cable was, it's basically something that contains light that's bouncing around. It looks like this. It has some radius A here, and this would be the fiber where all the ricocheting takes place. Then it has a cladding around here, some radius B, and outside the cladding is a jacket. You don't have to worry about this. I'm just doing this for perspective. And these things are infinitely long, effectively. And inside this piece of fiber, the electromagnetic field, the wave, just ricochets back and forth all the way down the line. Y'all follow me on this, class? That's basically it. Just like a rectangular guide, it ricochets. Now, here's the crazy part. This fiber here is dielectric, and this cladding is dielectric. Y'all follow me? So before the boundary condition, we used this either E tan was 0 at the interface, or we said the derivative of E tan, really the derivative of the H field tangent to the actual interface was 0. Do y'all remember that for TE and TM modes, right? Here you can't do that. There will be a field that extends in there. It's called an evanescent field. I'm just giving you this, the basic perspective. You have to appreciate this for this solution to make sense the way he did it. So there will be a field here, but it dies off very quickly, and it's an evanescent field. What it means is no energy is going to propagate that way. Y'all hear me? It will not propagate radially outward. If it does, then you can't, then all the energy will not go down the guide, all right? It won't. Now, an evanescent field is sort of like this. If you think of a capacitor, right? If it charges up, there's an electromagnetic field in space around it, correct, class? But that electromagnetic field isn't launched, gone forever. If you want the energy you put into that capacitor, you can get it back out, right? The type of field that is would be termed an evanescent field, even though that's not exactly the term used. But an evanescent field does not propagate electromagnetic energy. It just appears there and then comes back from where it appears. Y'all follow me on that? Just appreciate this for now. There's more to that, but I really, if I take off on that, we'll be doing differential equations for the next 3 class periods. And we'll be doing Bessel functions and all the other things. And some of you may appreciate that. Are there any physicists in here? I've had them in here. And they're the guys that want to see that. Come up to my office if you want. All right, so that's the case. Now, here is the thing you have to understand about fiber optics. This is for fiber now, not slabs. What they normally do is say this, that you have a fiber like this, and I draw a line right down the middle. You can call this the Z direction, but it won't be important. So this is all fiber in here. Y'all with me? This is fiber. And the fiber has some index of refraction, NF, which is the square root of epsilon relative to the fiber. Just keep that in mind. Now, the way it works is this. Light comes in, this is what I was trying to do last time in a hurry. Light is going to come into this fiber at some angle with respect to the normal. So there's going to be some electromagnetic energy, and the polarization doesn't matter at this point. It'll be at some incident angle coming in. You might as well call this air, because that's what it almost always is. All right, so you got something here shining light on this. It comes in at an incident angle. Now, you know that it's going to bend at a different angle here, right? Y'all with me on that? You can call it what you will. I think in his book he uses theta B, but I'm not actually sure. Yeah. So call this theta B. Does he use theta I here or theta A? If you look.
It's A.
A? All right. I prefer, so this is really theta I. It's the incident angle. That's the key thing. Now we know it's going to bend here, and we'll get to it in a second, but basically at this point, the thing that dictates the second angle would be Snell's law. All right? Just remember that. Now here, it's going to hit, and it's going to hit at an angle here. In his book, he calls it theta C. All right? Now for fiber optics to work, here's the deal. When this light ray is coming in here, in the fiber, when it hits here, the actual angle of reflection, I'll show you this. I'll just call this theta, use theta C, theta R for reflection. This has to be 90 degrees for propagation to take place. Now I want you to appreciate this. Here, as the light comes in, if this angle is 90 degrees, right, there's nothing that goes that way. Do y'all follow me on that? So that's the idea. Now, we're going to disassemble this in a second, but here's the deal. You see how this angle, we can go through the math on this. But basically, depending on the value, out here there'll be, this is the cladding, and there is an N cladding, that's the index of refraction there, that's the square root of epsilon relative for the cladding. Usually these two values, the cladding and the fiber's index of refraction, are very close. Do y'all follow me on this? But the cladding will have a slightly larger value. And it means that when this angle is 90 degrees, there still exists an angle here that's not 90. Do y'all follow me? And I'll do the math in a second. So the idea is this. We want to find out what the largest possible angle for light to come in here is before it starts, it doesn't ricochet all the way down there. In other words, if it comes in at an angle greater than this, more at a glazing blow, then some of that light will propagate out into the cladding, and that mode will not propagate. Y'all follow me? This is the idea of this. So how do we do this? We start here at the interface between the jacket, between the fiber and the cladding, and we write simply Snell's law here. This is in the book, it's not difficult to see. So for Snell's law, and I'll just do this. So Snell's law is usually beta, and I'll call it beta of the fiber times the sine here of theta C would be equal to beta of the cladding times the sine of, and I call that theta R. But we know that's going to go to 90 degrees. Are you with me? I'm just showing you this for completeness, so you'll appreciate it. And it's important you do. And I'll tell you why, because in the real world, you're going to find out you'll be exposed to structures that will not have a simple fiber and cladding. They may have layers here. That's called a graded index fiber. Or they may have something, the reason they do that is a little more complicated, but it basically allows the propagation modes to have, I say a wider range, but that's not the right word. It'll be beneficial. I'm going to leave it at that. But you have to at least appreciate the reason why we're doing this. Right? So we set this angle equal to 90. That means the sine of this becomes 1. This becomes 1. And now we get beta cladding, which is omega, really, times square root of mu cladding, epsilon cladding, equal to omega times square root of mu fiber, epsilon fiber, times the sine of theta cladding, or theta c, according to the drawing. And here's the thing I'm going to just say, and I did it before. Again, the sine becomes 1 because it's at 90. The omegas cancel. Just appreciate that really we're now getting the physics form of this. So if it's non-magnetic, so mu relative will be assumed to be 1 for all materials, or this wouldn't make a lot of sense doing it in a magnetic environment. And that means this is the index of refraction, and this is the index of refraction, so we have the sine of theta c is equal to simply the index of refraction for the cladding over the index of refraction of the fiber. And write this down. N fiber is greater than N cladding for this to work, or it won't work. And that N there is just the index of refraction. Usually what we talk about is the density of the medium. The larger the value of the intrinsic, or of the index of refraction. In other words, the larger the value of epsilon, the more dense the material is. And the way it's usually described in basic physics is that the more dense media causes the greater bend towards the normal. That's the bottom line. In other words, for this thing, if this media here was more dense, then this angle's bend would be less. It would be closer to the actual perpendicular. You all follow me on that, class? So that's the reason why. This is the first thing that determines it. Now, if we take a look at this just for a second, look at this drawing, Roy Whitmer's drawing. And I want you to appreciate this. You all see how the sine of that angle is the cosine of this angle, because that's a 90-degree triangle? Just think about it. Now, if you think about this, if we take a look at the cosine, well, look at this. If this is some dimension, call it b, then b over the hypotenuse is the cosine of this angle, which is also what? The sine of this angle, isn't it, class? Just trying to make sure you see it. So I can say that this becomes cosine of theta b. Can you tell me? Just tell me to be quiet or shut up. Who can see who's talking first? It's my department chair, leave me alone. All right, they left. Thank you. All right. You all with me on this? That's where we want to be. Now we have it in terms of angle B. Block that one. These are the steps, and this is not hard to follow. So now I use Snell's law here. Now I put this as air. Almost always it's air. It means the index of refraction of air, right there, call it A, is just 1. You all with me? Because the square root of epsilon relative is 1 for air. Therefore, the index of refraction is 1. So I'll just go right to the actual physics form of Snell's law, which means if I have A to A times the sine of theta A, that's equal to the index of refraction of the fiber times the sine of theta B. Are you all with me on this? Now here's the tricky use. There's probably a lot of different tricks. Y'all agree with that, by the way? I'm going to assume Na is 1. It's air. And that means the sine of theta A is equal to eta F, or the index of refraction of fiber times the sine of theta B. And now the trick is this. It's not really a trick. I want to find some clever way of replacing that. Well, what do we always do? Just remember this in engineering. Whenever you've got a cosine of the angle that you want the sine of that angle, then you know that cosine squared of theta plus sine squared of theta equal 1, right? Y'all with me on that? And that means if you're thinking about strict positive here, that the cosine square, or just cosine of theta, is equal to square root plus or minus square root of 1 minus sine squared theta. Y'all follow me? All right. Now, I got cosine there, and actually I can do it in inverse on this. I can say the sine of that angle, the sine of theta, there would be equal to square root plus or minus the square root of 1 minus cosine squared of that angle. Either one works. You agree with me? So I got the cosine there. Well, if I square it, y'all follow me in this? We're going to take the positive root because it's the only one that's logical to take. If you take that and you take the cosine there and put it here, you get the sine, right, of that angle, which is theta b, is equal to, we'll use the plus root, 1 minus the cosine squared, which is just nc over eta, or nf squared. Y'all see that? Class, with me on that? You know what I'm saying? The only thing I've done here is, I got a cosine, right? That means I have, the cosine of that is nc over nf. Well, there's a cosine here, isn't it, in this identity? So just replace that cosine by nc over nf. It's squared, that's the sine, right? You'll notice there's the sine right there, isn't there? All right, that's what I want. I want everything in terms of theta a. So then I find finally that sine of theta a, this is where it gets important, is equal to n fiber times sine of theta b, which is the square root of 1 minus nc over ns squared. Just take a look at that. There's nothing magical here. I just put that, stuck it in an equation, right? Y'all with me? You follow me in the far back, guys? All right, now, at this point, y'all see if I multiply through, bring nf inside, it's nf squared minus, there will be nc squared, right? And then I get this. Square root of nf squared minus nc squared, those are index of refraction, is the sine of theta a. And I want to make mention of the fact, if for whatever reason, those are n's by the way, for whatever reason, if that wasn't air, in other words, if the index of refraction of the incoming wasn't air, then you would simply divide this by the index of refraction of whatever the material is over here. Y'all with me on that? But routinely, I don't know of a situation where it's not air. And the reason is usually what happens is, if you have laser light or something over here, it's just flashing on this. Y'all follow me? How many people have been exposed to fiber optics? Laboratory work, co-op? If there's one thing you do know, if it's real fiber optic, alignment of the laser light is critical for fibers to be excited and the light to propagate. Have you ever done this stuff? We used to have a fiber optic EMC lab upstairs. It had a laser in there. It was a long story. But if you misalign this just a little, like the fiber from the light, the incident light, then nothing propagates. So if you got something where there's a little bit of wiggle room here and it's in a vibrational, in an area with a lot of vibrations, then it will not work. Y'all follow me? So it's real important for alignment. So what they do in fiber optics is this. They assign a figure of merit to how close you have to be to this angle. What they do is call this the numerical aperture. This is called NA. It's in your book. It's just the sine of that angle. Now, if you want that angle, you can take the inverse sine, or the inverse sine of the square root of the two things squared over that. But the thing is, that's a small angle. So they usually take the sine of that angle. And the general rule of thumb that I know, and by the way, I'm not an expert on fiber optics, so if somebody's dad or mom works for Corning Glass or something like that, and they tell you something different, then let me know. But as far as I know, the way they gauge how, quote, good a fiber is for the purpose is by this. The larger this value, the better it is at propagating light. Because you don't have to line it that well. Y'all follow me? Think about that. If that thing, say that angle is 1 degree, right? Well, a 1 degree difference in the actual direction light comes from a light emitting diode. Remember, that's coherent light. All right? It comes in one direction. Well, that's not much wiggle room, all right? So what you would like to, then if you've got that, then you have to basically, you know the term potting? When you actually put things together and then you do a fill with something, like a glue or something, it'll harden so it keeps everything rigid so it can't move, all right? Then they pot things and stuff like this. That's an extra step and more money. They would prefer this angle large. However, I'm just going to say this, telling you the facts, all right? You can't get a lot of difference between these two. It just doesn't work. All right? When you talk about fiber optics and stuff like this, remember, it's going to be silicon dioxide and then something outside with some doping on it to change the value and give the intrinsic impedance, or I'm sorry, the character or the index of refraction at the wavelength. All right? Now this is real important. Well, all that stuff has to have the same thermal expansion coefficient. It has to basically be the same stuff, and here's why. You got a long bunch of stuff on a cable like a, you got a core with a certain bunch of material. If the thermal expansions and things like this aren't the same, then the stuff will actually move and shear apart as there's temperature changes. Remember this. So they try to make it as close to the same material as possible. And that causes a lot of problems. Well, not problems. It causes more steps in the fabrication. I'm just telling you this is not easy to do. It's a material science problem, really materials engineering. Making fiber is no joke and it's not easy. Now, that really, you're going to see in Whitmer's book, he's got a few other formulas, but I'm telling you, that's the one you remember that's important to know, all right? And it's not hard to understand, yeah.
What is that in the denominator over there?
I just put the index of refraction right here, I can put it. And this would be the index of refraction out here. I can call this just N0 is index of refraction where the light source is. That's all it is. Typically it's 1. I'm just leveling. I don't know cases it's not my self. I can imagine for, you know, stuff that they send to Jupiter or something, they're going to have a pressurized environment. It may not be, but generally speaking it is. Anyway, that's the key thing. Now, this is for something, the fiber I'm showing you here is really, it's all fiber of a given index of refraction, then it's all cladding and then jacket, right? Thickness of the cladding is not of importance, not at all, really. I mean, it has to be, it can't be, you know, real shallow, but the wave dies off fairly fast in here, the evanescent mode, and you don't have to worry about it. Now here's the other thing I've got to tell you. When you have fiber optic stuff, there's something called graded index that he mentions in the book. It's called GRIN, graded index materials and stuff. But what will happen is they will have a transition from the fiber index of refraction to the cladding, and it will change, not instantly, but it'll change gradually from one to the other, right? That happens. There's a lot of problems with that, but there's a reason for it. Most of the time what they do is they have the fiber in here, and then they'll put a layer just on the other side of it that will have a slightly different index of refraction, and then another one, and it will gradually approach the cladding, but it'll be over a very small region. Just appreciate that can happen. That's called graded index material, or graded index fiber. The term is GRIN. We don't worry ourselves about the material science aspects. You just have to appreciate what goes on. Primarily, that's the thing you worry about. Now, in his book, I want to make mention of this, and I'll tell you what I consider important. The thing I just talked about is equation 7.109 at the bottom of page 410. It's a very straightforward thing. This is not hard to understand. A logical thing you should be thinking was, what kind of questions would you ask? That's a logical. Right? So I might ask, what would NF be if NC had a certain value and I wanted the numerical aperture to be something? In other words, I give you two of the three possible values in here and you solve for the third. Y'all with me? It's straightforward. There's nothing tricky about this, but you do have to appreciate if I wanted that angle, the maximum angle that light could come in, you'd have to be able to calculate it from here. Y'all with me on that? Now another thing is, I could ask a question, and this is a logical question, that if I had a piece of fiber, like so, there's the center, and I had a laser light like so, and I gave you the dimensions, all right, where I gave you, say, the standoff distance D, and I would have to give you something, say, this distance, A, and I asked you to tell me if that would propagate or not. You hear me now? You would have to look at this angle right here. And if that angle was greater than the allowable angle, right there, nothing propagates. Do y'all follow me? If it was less than, it would propagate. And that's really the issue here. Will it work or won't it? It's binary decision, has to do with that. I'm not an expert on this, but I want to tell you that's what it comes down to. Dr. Wentworth's book also talks about graded index fiber in 413. Then he shows you sort of an overview of some fiber optic, really it's a cross section of a fiber optic gallium arsenide laser diode. And he shows you a few things about optical detectors. The problem is it's at a level where for you to really appreciate this, you need the basic fundamental equations, Maxwell's equations and the solid state equations, then arrive at these solutions so you can see how all this fits together. I did want to say one other thing about fiber optics before I leave this. And this is not, hardcore mathematics, it's just the facts. When you have fiber optic tubes, I'm going to just erase this. This is unlike waveguides, conventional waveguides. We know that like coax cable and conventional waveguides have a constant frequency that's going down, right? They modulate it with FM if they want to communicate, and for radar signals, they kind of pulse it. So it's on and off. But with fiber optic guides, they send packets of light, little corpuscles of light that we call photons. Y'all heard the term photon, everybody? It's just the smallest little bit of light that can be predefined exactly. It has a polarization, it has momentum, it has a frequency, or wavelength. So when you take a look at a fiber optic tube like this, okay? And we took a snapshot of time, say t equals 0. Let's assume everything's propagating down here. What you'll see is in a region here, there'll be a whole bunch of photons that are moving at the speed of light. Then there'll be nothing. Then there'll be another packet with photons moving. Y'all follow me? Now I'm trying to show you this. Now as these things move, like with anything that you know about in physics, these things are moving at approximately the speed of light down that glass tube. They disperse. And what really happens in Wentworth's book, he shows you if the wave starts like this, so at t equals 0, very close to the photodetector, I should say the photo source, the laser diode, there's just real sharp, there's nothing here, and then there's photons here, and they're moving at the speed of light. Over time, what happens is the photons, the density of photons, if this was density of photons this way, and this was the actual position of them, if you took another snapshot of time further down the pipe, you would see some of these things slowing down slightly, some of them increasing slightly in speed. There'll be a very small amount of attenuation. Y'all follow me? So that means with fiber optic, because you're sending bursts of light, right? Send a whole bunch of light, then no light. Whole bunch of light, then no light. There comes a maximum distance that you can send this before this stuff starts looking like this in terms of the densities of the actual, if this was the density function, probability density for photons of a given frequency, and this was the spatial dimension z, then they start to blur together and you can't distinguish where one began and one ended. Y'all follow me? Now we don't get into that, but it's called, you have to understand, that's caused by dispersion. So what they normally do is, they figure out the maximum distance that they can have a fiber optic tube, and this is true fiber now, before they need what's called a repeater. You don't know the term repeater? What it'll do is it'll take this and then it will convert whatever comes into a 1 or a 0, and it knows what's being sent before it, and then it will sharpen up the signal and resend it. So all that blaring goes away and it starts afresh again. Now there's a time delay, and repeaters, it's very slight, and repeaters cost money, but the beautiful thing with fiber, unlike RF cable, coax cable, you need these every maybe, nowadays, 10 to 20 miles, I think is fair. Does anybody know for sure? I think it's 10 to 20 miles. It used to be every mile and a half, 2 miles. What is it? You know?
Yeah, it's about 10 miles.
It's no, and it depends on the type of fiber. This gets into these areas, dark areas that I really don't know about, because the military has all sorts of specs that do not apply to civilian stuff. But most fiber optic civilian sources are about 10 to 20 miles before they need a repeater. Now, there's reasons I say that, because you see, if you go through mountains and stuff, the actual total length of the cable may be maybe a lot longer than the actual straight line distance between the 2 points. So it's normally, I think, about, I want to say like 36 or so kilometers in true distance they need a repeater, and that comes down to, I don't know, somewhere like 20 miles, about something like that. All right, so just appreciate that for what it's worth. Some of you will be working with fiber optics. Has anybody ever laid fiber optic material? I mean, true ones? You did? Was it in this state or in Georgia?
It was in this state.
When they did it, did they have like a 10-foot high spool, or was it bigger than that? Normally this stuff, I mean, it has a very small radius of curvature, very large radius of curvature. There's not much bend, and they lay it out in these large, after they dig the ditch, they put it down. Do you recall?
Yeah, it was like, I was just doing like one side job with it. Like I had a guy that was working with, and it was something like, it was pretty high.
It is an amazing, it's not like a tight little bundle they just unwrap. It's very large, because this curvature on those things becomes, they can't bend it much. The rate that it bends is very small. I'm trying to give you an appreciation for this. I know you probably like to see the problems I'm going to ask. Basically what I showed you is what I'm going to ask. Now, in his book, he does give this other formula about this. And I don't get to the repeater distance. I'm going to tell you right this. We're not going to do the rise time budget. I know it's in there. There's so many parts to that that are not satisfying. We're not going to do optical detectors. Just appreciate optical detection is nothing more than a standard transistor where the base junction is going to be illuminated by the light, and that's how it creates whole electron pairs. That's all it is. But in his book, he does do one thing that I want to share with you. And I don't get into this, but if you have your books on page 408, what he does, without an explanation, because this has to do with the solution of Maxwell's equations for cylindrical coordinates, he gives you an equation for step index mode. That's the type of fiber we are talking about. How many propagating modes will be present? This is equation 7.104. And he talks about a cutoff wavelength, lambda sub 0. Now I'm going to talk about the cutoff wavelength and why that's there and how come it doesn't make a lot of sense. I'm trying to do this in a way that, at least if I'm sitting where you are, I want to know what the professor's thinking when he's saying stuff, because some of this makes no sense to me. I'm just telling you. So appreciate this. I know if you don't think it does, I don't either. But I know enough that I know how this stuff works and why it works. So let me just tell you this. Other reason, by the way, the reason I asked about Georgia versus Alabama, there are different companies that own the right of way for fiber optic distribution. And here, I think it's Verizon right now. I'm not sure. But there are other groups that have that. And whoever has the eminent domain, they lay fiber their own way. And they're different, there's different sizes. So I don't know if you guys know this, but the utilities, these are basically government oversight utilities, all of them, right? And they get right of way and they lay cable the way their cable, and it's not always the same size. I'm just telling you, there's some crazy things, because when you think you know it, and you go somewhere else and find out it's quite different, especially for some of the equipment they use. Okay, now, getting back to this, and let me try to make sense of something. I'm gonna just mention something, I'm gonna mention the slab waveguide, but it'll apply to the circular dielectric waveguide as well. In Whitmer's book, he talks about a slab waveguide. And this one will trouble you. It should, if you've been reading. But for a slab waveguide, he just says, let's assume we have an infinitely long slab here, and there's some index of refraction, or beta, it doesn't matter, but index of refraction for the slab, and there's some index of refraction, and you can call this the cladding, but it doesn't matter. This is going to be planar, okay? And we're going to say that optical energy is just ricocheting down this guide as such. But now it's a plate, okay? It's hard for me to draw this effectively, but basically you have an infinitely long plate. In the real world, you wouldn't have that. You would have a very wide piece of material that would be made up of a dielectric material, and it would be surrounded by another dielectric material. And inside this thing, everything ricochets back and forth. Y'all with me? Now here's the thing. When I have something like this, if I just focus on that cross section for a minute, and I bring it back to the time we did rectangular guides that were surrounded by conducting walls, the boundary conditions were real easy. They were just the tangent electric field goes to 0, or the derivative of the tangent magnetic field with respect to the normal will go to 0. I say those are simple, because these aren't. Here's what really happens. If we look down that guide, and I'll make it this way. And this is the thickness of the guide, all right? And stuff's propagating into the board. You can call this the x-axis. It really doesn't matter at this point. And this is the y-axis. And this is the fiber. Or, sorry, this is the dielectric. And there's a material out here, and you can call it, you can call it slab, and the cladding, and cladding outside. Inside here, if this is the origin, say right there, the equation del squared of E plus omega squared times mu of the slab, epsilon of the slab, times E equals 0 still applies. And out here, del squared of E plus omega squared mu of the cladding, epsilon of the cladding, E still applies. Now you don't have to know this. You don't worry about knowing this exactly. I'm just trying to show you something. Before, what did we do? We took that, we made some assumptions as everything's propagating the z direction. We took this and we solved it for the boundary conditions on the rectangular guide by setting EZ equals 0. That was a TMO. Do y'all remember that? Without going into details, right? And we had a hard boundary condition that EZ was 0 wherever the waveguide, at the ends of the cross section of the guide, or at the span, right? Here, it's not the case. So, when we write the solutions for these, we get an infinite series of sines and cosines with coefficients. Just appreciate this. Over here, we get an infinite series of sines and cosines with coefficients that we have to solve for. And the way we solve for is we equate easy, if it was a TM mode, at the boundary right here. And it is a pain. I'm just trying to tell you. That's why it's not in Whitmer's book. It is well beyond the scope. He shows you a little bit, but he doesn't go through get into the weeds. Now, something that happens here, and this should be intuitively obvious. For this particular fiber, I'm talking about slab guide. That's where the light's contained, in this region, all right? It bounces around. In this slab waveguide, because the boundary conditions do not go to 0, if you would just look at the magnitude of EZ, if this is where the boundary is, And we just plotted, don't worry about writing this down, the magnitude of EZ. Remember, that's E field in the Z direction, in the direction of propagation. Well, it wouldn't go to 0. You wouldn't have a half-wave. What you would have is this. All right? I'm just trying to give you an appreciation. Now, the lower the frequency, the more gradual this thing comes down. All right? I know you're thinking that seems insane. That's what really happens, all right? And there is no cutoff frequency for the O mode. That's the lowest order modes that can propagate. In Dr. Wimmer's book, he calls it TE0 or TM0. And to you, you're like, huh, what does that mean? It means this. No matter how low the frequency, things will propagate. However, here's the thing, just listen to me. The first cutoff frequency for the O mode, and it'll be in his book, it'll be the lowest. That is the frequency that you have to be at least around so that the energy will stick inside this guy, all right? If you don't have a frequency near there, and I can't get into the math on this one, then more and more energy will just go out, it won't stick. Now you all know how wherever there's a discontinuity, that's where waves travel. All right, I mean, that's the thing that kind of grabs them. If you just have a long wire and you blast it with electromagnetic energy, where that wire is on the surface between the copper and the air, there's all sorts of electromagnetic propagation. There's creeping waves and there's all sorts of stuff. But that's where the energy is, at the discontinuity. It's the same here. The energy will reside between here at the discontinuity surface. And the physics of that gets way beyond what we're going to do here. But it's interesting to do. In the higher level courses, we do slab waveguides and circular waveguides in detail with that. But that's like, honestly, it's about 3 or 4 lectures for graduate students that have had a lot more math than you have. So I'm just going to try to give you an appreciation for this. So what do you need to know? It's the next logical question you have. And the thing is, equation 7.103 and 7.104, only for the purposes of solving some problems and an appreciation. This is for graded index fiber, or I'm sorry, it's for step index. Step means it's binary. It's either fiber or it's cloudy, but it doesn't gradually go there. So this is the lowest order, or the smallest wavelength for only one mode to propagate. Now what it's really saying, without saying it, is that frequency tells you that if you're at that frequency or less, only one mode propagates. If you're greater than that, it's lambda naught, so it's really the speed of light in the fiber divided by frequency. But it's really the threshold, just remember that. And unlike a rectangular guide, fiber optic guides will allow propagation less than cutoff frequency. It's just they won't be that efficient. They will start bleeding off the energy. But it's so far beyond what we can deal with here. And in what we're supposed, he does not discuss this at the level I think it should. Did anybody look at the discussion of the waveguide that I put up there on YouTube? All right, if you did, he did the ricochet thing where he just got the phase fronts to have to be constructed. That's another way of doing this. It just results in the same type of solutions, okay? There's nothing fancy about it. So I said all that just to tell you this. I'll give you some problems. Now I want to tell you where we're going. Yes?
When, I guess application-wise, when would it be beneficial to use a slab rather than just the regular circuit?
Okay, that's a very good question. When are you going to use fiber optic? Slab waveguides are used on microelectronic circuits when you have lithography that's always basically a sandwich. You put down a layer of something, then you etch it, then you put down a layer of something, and you dope it. So when you're you can't build a fiber that's round inside a VLSI processor. Do y'all follow me? So they'll put a slab waveguide to connect an optical diode to like a or better yet, an optical or an LED diode to a fiber optic tube that will then connect to to a dielectric slab, then connect to fiber optic tubing. All right, that's something I'd prefer to present. I still haven't brought down a waveguide, have I? Guys, threaten to sue me or something. I showed you a picture. I know I'm almost out of time. Let me just tell you where we're going. No matter what I do with this lecture, I used to bring stuff down here all the time, little show and tell. It doesn't hit home until you actually have to do something with fiber optics because it's so abstract, a lot of this stuff. Have you ever worked with light or with any kind of light sensing diodes or anything? Photodetectors? Or if you have, then you're ahead of the curve. Most people haven't. I want to tell you, we're going to do antennas. Please show up on Friday. Another good question is, do we have a quiz Friday, right? Let's see. I'll give you a quiz on rectangular waveguides that are conducting, all right? I'm trying to be as clear as I can. Got it? Not fiber optic, the actual conducting ones. And I'll give you something where, remember that problem I gave you with the replaces a transmission line, guys? Think that way. Got me on that? I'm literally telling you what's coming your way.
It was the replacing transmission.
Do you remember how we had a guide that looked just like a transmission line, only now the guide impedance was something you had to calculate and the value of beta was something you had to calculate? And then you had to calculate the reflection coefficient, then you had to make sure you know what you're doing from a source voltage to power. So
Oh, yeah.
here's the, I'm telling you what punch is coming and which way it's coming. So please just come to class and be ready. And do me one other favor too. If you or know of anybody that's sick or are sick or anything like that, go get tested. I think I told you I had to get tested, didn't I?
Yes.
I've been exposed. I've been negative every time, thank God, but yeah.
You said you were going to give us a handful of waves.
No, not for this. I mean, the only thing I'm going to ask for with waveguides, I'll give you that equation for Zn where it's Z0 times ZL plus J Z naught tangent of beta Z times L over that. You know that one? I'll give you that one, but you're going to have to know how to calculate the impedance and the air field, all right? And the reflection coefficient and all that. I won't give you that. Fair enough?
I think so.